started, because I don't know if these people are coming back or not. So 11.1 sequences, you should be on page 111. Yeah, page 111. Oh, look at that, page 111, 1.1, what a coincidence. I did that on purpose, you're right, I totally planned the entire packet to make sure that 11.1 would start on page 111. You figured me out now, Daniel.
Sequence over there.
Okay, so a sequence has a nice short, sweet definition. Is ordered list of numbers. Ordered meaning you can't rearrange them. It's a list where the order matters. So if I asked you, all of you, your ages, I could list them all and rearrange them and it would be a different list. But if they were in order, like from where you were sitting, for example, I can't rearrange them because his age is not the same as her age, or maybe it is, but it would mix it all up. So any ordered list of numbers. So for example, I might start with this list of numbers. 16, 8, 4, 2, 1, 1/2, dot, dot, dot. Here's an ordered list of numbers, just some numbers in an order. So the order matters because what we'll do is we'll talk about the terms of this sequence. This is the first term, which is the first one in the list. The second term, the third term, the fourth term. We'll talk about the general term. So the terms are just talking about individual ones. And they all have numbers, the first term, the seventh term, the 100th term. And the hardest part about sequences is recognizing a pattern. Because quite often when they put dot, 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 that's telling you that this continues forever. So usually our sequences are infinite. And some of you are looking at that going, oh, I already see the pattern. And others of you don't see it, are looking at it going, you don't see it yet. And I can't teach you how to recognize something. Right? That's the hardest thing. Either you recognize it or you don't. Some people have to play around with it a little bit more. My example of that, maybe I've used it with you guys before, is I could describe my grandmother to you in lots and lots of detail. And then if she walked in the room, you wouldn't know for sure that it was her, but I would recognize her and, oh, that's her. You might go, oh yeah, based on the description, it could be her. But until you actually knew it, so it's hard to teach someone with explanations. So you kind of just want to look for some relationships. And some people are quicker at that than others. Who sees the relationship here? Yeah, I got almost 2/3 of you, I'd say, see the relationship. That's good. So what is it, Jose?
Divided by 2.
It's just divided by 2. Whatever this one was, the next one is half of that. The next one is half of that. So if you don't see it now, you're, oh, now I see it. You kind of have to play around with it and look for it. So we talk about the term. So this one right here, we might label as A1, the first term. The first term, that's A sub 1. We don't always start at 1, sometimes we start with 0, but usually we start counting at 1, the first term. So this is 1, 2, 3, 4, and this is A5, the fifth term. Oops, double arrows here. Double arrows, that's the fifth term. 1, 2, 3, 4, 5. What's A7? 1/4, right? Because we just keep dividing by 2. What's A9? 1/16. Because you divide by 2 and divide by 2 again, right? Well, you keep doing that all day long. Well, you want to know what A100 is?
Yeah.
Is that what you said?
Yes.
What is A100? That's a good question. He brought it up, don't blame me. You're thinking? Thinking's good.
Could you do 2 to the negative 100?
You're close. So he says 2 to the negative 100. Basically, you're multiplying by 1/2 100 times. Not quite, but you're so close. How many times am I really multiplying by 1/2? I started with 16.
Oh, shoot.
And I only have to take half 99 times, right? Not 100 times?
Yeah.
So my 100th term is, I'm gonna start with 16, and then I'm gonna multiply by 1/2 99 times. It's a tiny, tiny number. I can't write it as a fraction even, because 2 to the 99th is huge. Can somebody give it to me in scientific notation? Your calculator can do it.
1.014 or 30 for,
Say again. Negative 33?
yeah. Maybe 31.
Negative 31?
That's this one.
What is that? Essentially zero. It's 0.00000000001.
My bad, I lied.
You lied?
Yeah.
Uh-oh.
I multiplied it by 2, not by 1/2. But
2.5 times.
yeah, 2.54 to the negative 29. My bad.
It's okay. 2.54 to negative 29. Someone agree with him? Or disagree with him? No, we disagreed with him last time.
2.524 plus 1.
E to the negative 29?
Yeah.
I'm glad you caught that. And if I did that, in here, there's 28 zeros. 28 zeros here. It's a tiny number, which makes sense. Every time I divide by 2, they're getting smaller and smaller and smaller. So we could find any one that we want, any term that we want. That's just a notation and how we talk about them. So a lot of times we write them with a formula, like we have in example 1. Oh, before that. Sequences can be infinite or finite. Infinite, like this one, ... implies it just goes on forever. But sometimes a sequence might just have 20 terms, starting with the first one, ending with the 20th, and that's it. So that would be a finite sequence. Most of the ones we see will be infinite. And they don't have to start with a 1 or the first term. Sometimes they start with A7 as the first one, and they go count from there. All depends on what you're working with. I'm going to show you some examples of notation so that we don't freak out. We were talking during the break. The hardest part about chapter 11 for a lot of people is the notation. So make sure you ask questions about what it means. So example 1. Oh, did I switch back to the dead pen? I think I did. Example 1, A, has these curly brackets, n plus 1 over n squared, n equals 1 to infinity. And the directions say to write out the first 5 terms of the sequence. So this just tells you, these curly brackets tell you it's a sequence. This tells you how to find each term. The first term you're going to plug in, you're starting with 1. You're going to plug 1 in for n. The second term you'll plug 2 in for n. The third term you'll plug 3 in, and so forth. And this says it goes on forever. So they're only asking for 5 terms, but there's an infinite number. Everyone okay with that notation? So the first term is going to be 1 plus 1 over 1 squared. I'm going to leave it like this first, and I'll simplify it. Because I started with 1, plugged in for my n. Always counting numbers. The next one will be n equals 2. When I plug in 2, it'll be 2 plus 1 over 2 squared. When I plug in 3, 3 plus 1 over 3 squared. Then the fourth term, and then the fifth term. Directions asked for the first 5 terms. Yes?
If it was to ever ask for that, like in our lab assignment, would you want it in terms of that, or do you want us to simplify it?
Oh, we're gonna simplify it. I was just starting here. Yeah, so if they asked just for the first 5 terms, really I'm just looking for a list of 5 numbers. So kind of like this example I gave you over here. Here's a list of the first 6 terms, right? So just make them in a list. So when we simplify them, we get 2 3/4, 4 9ths, 5 16ths, and 6 25ths. Just simplifying each of those. So those are the first 5 terms of this particular sequence. notice that if we had started with this, figuring out that formula would have been a little tricky. You can kind of see the denominators, I think you can, right? Can you see the perfect squares, 4, 9, 16, 25? You could get there eventually. That's the part about recognizing that I can't teach you. You kind of have to just play around with it and do some trial and error. We're going to be doing some of those a little bit, working backwards with, here's your list, what's the formula? So what's different about question B? 1B.
Starts at 0.
It starts at 0, which means your first term actually is the 0th term, right? We're going to plug 0 in for it. So question B looks like this. -1 to the n plus 1 over 2 to the n. And it starts with n equals 0 to infinity. In the same directions, write out the first 5 terms. So what am I going to do? Plug in 0. -1 to the 0 plus 1 over 2 to the 0. That's the first term, even though it started with 0. They call this n the index. Its index is starting at 0. And then we'll plug in 1. And we'll keep going till we have 5 of them. Plugging in 2, plugging in 3, and finally 4. Get the first 5 terms of that one. I only have to go up to 4 because 0 to 4 is actually 5 of them. What are the numerators doing? They're alternating, right? This first one turns out to be -1 to the 1, which is negative. But this is -1 squared, which is just +1. And then I've got -1 cubed, which is -1. Positive. So we actually call this an alternating sequence. When you have those -1 raised to those powers where they change positive, negative, that's called alternating. So this is -1 over 1. Simplifying here. +1 over 2. -1 over 4. +1 over, I lost my place.
Over
This one, 8. And -1 over 16. Those are the first 5 terms. Kind of refreshing, it's not quite as messy as polar coordinates. This I would simplify just to make it a -1, this first one. But here's the first 5 terms of this. Yes.
It's called alternating sequence.
This is alternating, yeah. So anytime the signs are changing, positive, negative, it's called alternating. Whether it starts positive or starts negative. And you'll usually recognize that they're coming because you'll see these -1s raised to the power, or a negative number of some sort raised to the power. Alternating sequence. So far, so good. Every section starts off kind of nice, doesn't it? I think this one stays nice, really. A lot of vocabulary, but nothing too bad. So really what we were doing with these is we were treating these formulas kind of like functions, right? Just plugging numbers in for x, like x's and y's. So we do that a lot. We write this, the part on the inside here, we call that the general term. So in this case, the first example here, we would say that an equals n plus 1 over n squared. That's how you find we call it the nth term. Any term you want. So if you wanted the 17th term, you'd put 17 in there to get that answer. The same thing over there, the general term. Now we're going to work backwards. We're going to start with the list and come up with the formula. And this is the part where once you see the formula, you go, oh, I see it now. But the recognizing part's tricky. So looking at example 2, we have a list. and we want a formula for the general term of this sequence. So example 2 has a sequence which is a finite sequence. It only has 4 terms in it. Only has 4 terms in it. There they are. And we want a formula for an. So they're hoping that we can write something like this, like that. So those of you that see it already, please be patient. What do you notice about this sequence? What are some of the patterns that we recognize? Pieces of it at a time. Yeah, Jose?
Alternating.
He sees alternating.
And the 3 is squaring at the bottom.
Ah, okay. He sees alternating. Right, sees alternating. And he sees powers of 3 in denominator. Now, you don't need to write all this down when you're looking for the formula, but I'm writing it down to help you see what the formula ends up looking like. What else do you notice?
It's just changes signs, it's just multiplied.
Changes sign, that's the alternating part, yeah? What were you saying?
It's just multiplied by negative 2/3 every time.
Ah. So Daniel says it's multiplying by
What?
negative 2/3 every time.
Yeah.
Agree with that? So we saw alternating, we see powers of 3 in denominator. Does this make sense? He's multiplying by negative 2/3? Okay, what else? Just brainstorming. What if Daniel hadn't told us this? We talked about alternating, we talked about the denominators. What do you notice about the numerator? Yeah?
The numerator is top right, is doubling every time.
Yeah, the numerators are doubling, or powers of 2. So when you're trying to come up with a formula, these are the kind of things you want to start with, like what's the relationship here? And I'm going to hold off on Daniel's because it's going to get us to the answer a lot quicker, which is good. But some people can't see that one off the get-go, so we're going to hold this one off for a minute. Forget this one, just for a minute. If you need to, look at all these 3 separate things separately and you'll get to the right answer. So if it's alternating, the first thing I'm going to think of is maybe I've got negative 1 to the n. Some powers of negative 1, that makes it alternating. And so just looking at that piece, let's say I start with n equals 1. So how many terms did I say I had? 4. Does that work? Just for the alternating part. What's negative 1 to the 1? Negative 1. Is my first term negative? Uh-oh. See the problem? If I plug a 1 in there, my first term's not going to be negative. So we could either add or subtract 1 from here. That's all we have to do. Do we have a plus 1 over there? We did. We had an m plus 1 over there. So you can just kind of tack that on to make it be the correct sign. If our first term was negative, I could have left it the way I had it. But now when I plug 1 in there, I'll get negative 1 squared, which is positive. And when I plug 2 in there, I'll get negative 1 cubed, which is negative. So you can adjust this as needed to make it come out the right way. Yeah, Jamie?
Could you just start at 0 instead?
Oh, or we could start at 0. Let's talk about or. I like this. Or, Jamie says she likes the negative 1 to the n, and she wants to start at 0, which would mean we'd only go to 3. Does that work? Because when I plug in 0, I'll get positive. When I plug in 1, I'll get negative. So the good news is either way it's going to work. What comes next will change a little bit. So I'm going to finish this one first. All right. So powers of 3 in the denominator. So my first thought is 3 to the n. 3 to the n, that's what I'm guessing. Is this 3 to the 1? 3 to the 2? 3 to the 3? No? Yes? I see both people saying yes and no. Is there a 3 to the 1 down here? No. And there's not a 3 to the 2, and there's not a 3 to the 3. What's the problem?
You're just multiplying the two, it's not actually.
Well, I'm not
You
adding.
do a 1 and then a 1 minus 1 and then,
That's minus one.
Ah, n minus 1, so he sees it. This is really 3 to the 1. This is 3 squared. Sometimes it helps to rewrite these, by the way. What's this? 3 to the
n minus 1.
3 to the 0. So it's actually n minus 1, right? It's 1 less than our n. So we could put a little minus 1 in here to make that work. And same thing happens with the powers of 2, right? Because we have 0 2s, 1 2, and so forth. So we would have to also have 2 to the n minus 1. Sometimes you just need to write down a formula, plug in a few n's and see if it works, and then adjust it accordingly. Do we agree that this one will give me that sequence? When you plug in 1, you'll get positive 1, 2 to the 0, 3 to the 0, that's just 1. When I plug in 2, negative 1 cubed, that's negative. 2 to the 1, 3 to the 1, so that's 2/3. It'd be easy to like list them all out. So that one works. Let's go back to Jamie's way though, I like it. She wanted to start at 0. If you start at 0, it's so much nicer. It's because she saw it. Again, I can't tell you which one is the C. If you start at 0, the negative 1 to the n worked. Notice if we start at 0, those exponents are just the n's now, right? 3 to the 0. So we could have just left it as 3 to the 0, sorry, 3 to the n, times 2 to the n. That gives you the same answer. So if this problem were on a test, some people are going to write this down as their answer. Some people are going to write this down as their answer. I might get creative and write this down as my answer. Do this works now. Oop, I have to stop it here. I might write that down as my answer. Because I'm just being ultra creative and annoying. Or annoying and maybe a little creative. Or both. Does it work? I mean, I could be annoyingly wrong. Because what would I plug in first? Negative 3. So that'd be negative 1 to the 0, which is positive 1. And if I plug negative 3 in here, that's 0. Anything to the 0, that's just 1. So the first term would come out to be 1. And if I plug the next number in, it would be negative 2. That's the next one, right? Negative 2. That'd be a positive 1. That'd be a positive 1. I would just get negative 1 times 2/3. So that one works. There's an infinite number of ways to write these. That one's a little extreme. But one of the quickest ways to get there is to do exactly what Daniel noticed from the get-go. Instead of doing your numerators and your denominators separately, if you see it's just multiplying by something every time, let's just say that. Let's just say I've got powers of negative 2/3. We're multiplying by negative 2/3 every time? I'm just going to keep multiplying by negative 2/3. Bless you. If we write it that way, where should I start? N equals, do I want to start with 1? Or do I want to start with 0 or 2? What's n start with? 0. N equals 0 to 3. All of these are acceptable answers. This one was boring. And weird. Maybe not boring. Unnecessary. Oh, it's all relative to the definition of boringness. Questions?
Wait, so what does the top number mean again? Like,
This number?
yeah.
This tells you where to stop. So this says start at
Okay.
0, plug in 0, then plug in 1, then plug in 2, then plug in 3.
Okay, so 0 is, or like the M is just the first one?
Yes. Whatever's down here is the first one.
So it's not including it, right? It's just starting it there, and the 3 after, so it'd be like 2, 3, 4, not.
It's plugging in n equals 0, 1, 2, and 3. So it's a total of 4, but I'm plugging these 4 numbers in. Where here, on this creative one I made up over here, we were plugging in -3, -2, -1, and 0 to get my 4 terms. Up here, we were gonna plug in 1, 2, 3, and 4. So those are your n's. Is that what you're asking? Maybe? And sometimes the top number is an infinity because it goes on forever. But in this case, because there were only 4 terms. You're good then. Other questions? Okay, let's look at the next one. Oh, there's another one, darn it. There's another one. Must be one coming up later. Okay, so after that, it says there that we will be interested in whether or not a sequence converges onto a particular value. I have since erased my very first example. Remember the one that started with 16, 8, 4, 2, 1/2, dot, dot, dot. Converging onto a particular value meaning eventually what are those numbers approaching? So in this case, they're approaching 0, right? Remember we went out to the 100th term and it was almost 0? So the further out you go, the closer they're getting to 0. So that's what it's saying there. We'll be interested in whether or not they converge. And sometimes a graph can help. You can actually graph sequences on your calculator as well. So example 3 asks you to graph this guy right here, which was, I think, an equals, it was our one from example 1a. N plus 1 over n squared. Let's talk about how to do that in your calculator. Maybe we'll do it by hand first, then we'll do our calculator. We'll do calculator first. Calculator, you're going to change your mode to sequence. There's a sequence mode on your calculator. And then where you usually type in your function, you're typing in your sequence, and it automatically puts an n in there. You guys finding it? Play around with that for a minute or two, and then we'll talk about what it's actually doing for you. You should have a bunch of dots.
I'm just plotting the individual points. right?
It's plotting individual points. It's like your y values are your values for your terms. Your first term, your second term, your third term. We're going to put it up here in a minute. I want you guys to play around with it for a minute.
When you look at table, it doesn't even call it y, it calls it u of n.
Yes,
That's
Mhm.
normal.
it's counting with n's. And your table only counts by ones. It doesn't go with, there's no 1/2. You can't count by half. You can't have the 1.5 term. Doesn't make sense. See if you guys are getting a picture before I put it up here. Calculator is showing you a graph that relates each n with each an. So your horizontal axis are your n's and your vertical axis are your y's are your an's. So this was the sequence that we had done earlier over here. Same sequence that we had done earlier. We listed the first 5 terms. So I was helping some of you who couldn't really see the graph very well, and I had told you, I said, why don't you change it and just go a y minimum of 0 to 2? Because we already know that there's nothing past 2. It just keeps getting smaller after that. So if you change it from 0 to 2, it starts over here at 1, and the first term had a value of 2. And the second term had a value of 3/4. So it's kind of like ordered pairs where it's n and then the an. And the third term was 4/9, which is a little bit less than half. And the fourth term was 5/16. And the fifth term, so you end up with these little dots here. And you actually get dots. You don't get the dots connected because there's nothing happening in between there. There isn't a term at 1.5. But this shows you the pattern of what's happening to these terms. Where are these terms heading visually? Where are they going? So the ends are going out to infinity, and then the y values are heading towards 0, he says. Right? The further out we go, if we kept going with these, you can't see it because it's so darn close, it's approaching that axis. So as the ends are going towards infinity, the ANs are heading towards 0. Agree with that statement? So that's the question. The question will be, does this sequence converge? Meaning, does it converge to a limit? Does it go somewhere? This one appears to be going to 0. Right? Those values of the terms are heading closer and closer and closer to 0. There are some sequences that don't converge. They kind of bounce around and never go anywhere. Or some that go off towards infinity, they don't converge either. So it's really talking about limits like we did in calculus, or calculus 1, sorry. This is what it's all about on the next page. So the next page, on page 112, lots of words and symbols. It's actually a review of everything you did with limits in Calc 1. Except it's throwing in the words converging and diverging. So do we agree with limit notation that we had from Calculus 1, that in this particular example, the limit as n goes to infinity of our general term is heading towards 0? For this same example we just did? Yeah? So this is all that we're talking about. So we say it converges to 0. If that limit exists, we say it converges. If that limit didn't exist, we'd say it doesn't converge, it diverges. So that's the definition at the top of the next page. We say it converges, or we say it diverges. It's a convergent or a divergent sequence. The limits are just review of what you did before. The limit laws, which are the whole middle of the next page, are all the limit laws from Calc 1. Saying that if you have two terms, you can look at the terms separately when you're doing limits. You can look at the top and bottom of fractions separately. All the stuff you've seen before. I'm not going to spend time reviewing all those limit laws. But that's just a reminder, you can take those limits. Sometimes we'll even use L'Hopital's rule to find the limits to see if a sequence converges or not. And then the last thing on that page is what's called the squeeze theorem. The squeeze theorem. So let me tell you what I mean by that. So say I have these 3 sequences. I have a formula for AN, and it looks like 2 over 1 plus, let's make this work, 1 over 5 to the n. That's what AN looks like. And I have BN. I have no idea what BN is. And I have CN, I want to make sure I have them in the same order. Oh, yeah. And I have CN, which maybe is 2 over 1 minus 1 over 5 to the n. So here's 3 different sequences. They're messy. The first 2 are, the first one and the last one. And I don't even know what the formula is for BN. I don't know. But the question is, does this one converge? Does it converge? I don't know anything about it. Other than, the one thing I know about it is I know that it's somewhere between AN and CN. It's bigger than this, but it's smaller than that. That's all I know. Bn is bigger than this number, but smaller than this number. And I want to know whether or not it converges. That's the question. So this is the squeeze theorem at the bottom of page 112. I'm explaining what it says first with an example. It's not there. I made it up. You guys are looking for it. Squeeze theorem. See, it starts with this statement here, the squeeze theorem, an less than bn less than cn. So I've made up an example of 3 different sequences. I made up this example of A and C. I don't have a formula for bn other than I know it's in between them. And the question is, does bn converge? Why is it yes?
Because it says that AN equals CN, and CN equals L, something, and according to this.
Right, so yeah, what does it say? That's the question. Yeah, what do you thinking, Zach?
I was thinking because the denominators are opposite in sign.
Yeah, I did that just to make sure that my formula worked. It didn't have to be exactly opposite. So let me ask you a different question. Does AN converge? What am I really asking when I ask if it converges? I heard so what did it say? Does it converge to a specific number when n approaches infinity? So the question here, does AN converge, is the same as asking, does the limit as n goes to infinity of 2 over 1 plus 1 over 5 to the n exist? That's the question. Does that limit exist?
2.
It does?
2.
It converges to 2 because this part right here, I need another color. This part right here is going to be 1 over infinity, so this part's going to approach 0. And it converges to 2. So we know that this limit for an, 2 over 1 plus 1 over 5 to the n, equals 2. So an converges. How about cn? It converges to 2 also. Same reasoning, right? Cn is going to be 2 over 1 minus 0 when we take its limit. So this guy converges to 2. And this guy converges to 2. And this guy is somewhere in between there. It has to go 2. That's what the squeeze theorem is talking about. A visual of what's happening is your AN, whatever it's doing, these are not the exact graphs, but AN, let's put 2 over here. So AN is maybe doing something like this, converging to 2 like that maybe. My points as I go out towards infinity are getting closer and closer to 2. Cn is bigger, so maybe the Cn's are up here. Maybe they're up here getting closer and closer to 2 over here. So AN is approaching 2. Cn is approaching 2. These are the ANs. These are the CNs. And all I really know about Bn is it's somewhere in between there. It's always lower than this, but higher than this.
They're gonna converge, if they're looking to converge, that one has.
It has to converge. It's squeezed in between there, right? So I need something in between there. And they can go up and down, but if I always have to stay in between there, you see what happens? I'm trapped in there. I'm squeezed to head to the same limit. And that's what the squeeze theorem says. If you look at the notation, it's really scary. But it says, if you have this situation, and this sequence and this sequence converge to the same limit, then the other one has to go to the same limit too. Because how else could you go anywhere else if you're trapped in between there? Right? That makes sense. The notation doesn't make sense by itself. Let's picture it. Now I get it. Okay. The next page has another example of a graph that talks about a sequence that converges. I'm going to skip over that. But now let's just look at example 4. Example 4 says, do these converge or diverge? And there's, we can pull 4 on the board. There we go. There's 3 of them. Here's a beautiful, messy formula for a sequence. Plus. And the first one in question is, does this sequence converge? What am I asking?
Does the limit as x, as n approaches infinity? Is the-
Beautiful. Does the limit exist as n approaches infinity? That's all I'm asking when we ask about a sequence converging. So we want the limit as n approaches infinity of 3n squared minus 1 over 10n plus 5n squared. We've got to pull off our, dust off our Calc 1 memory on how to take these limits. There's 2 ways to do it. Who remembers one of the ways? And approaching infinity.
You plug in infinity.
We can't plug in infinity because infinity's not a number. We can kind of look at it though and see what would
What I
happen.
mean is like if you put infinity in the numerator, now.
You get infinity minus 1, so the numerator is approaching infinity. The denominator is infinity plus infinity.
It's gonna be infinity, infinity over infinity.
Right, infinity over infinity is undetermined. It is not 1, because the numerator could be approaching infinity a lot faster, like maybe it's 3 million over 1 million. And then it's 3 billion over 1 billion. They're getting bigger, but they're not approaching 1. So you don't know they're approaching 1. What do you do when you have infinity over infinity? You could use L'Hopital's rule. L'Hopital's rule is the one that says you can take the derivative of the top and bottom separately and then do that limit. Highly recommend using L'Hopital's rule. So if we use L'Hopital's rule, we can take the derivative of the top, which is 6n, the derivative of the bottom, which is 10 plus 10n, and then take the limit. What's the problem here? It's still infinity over infinity. So we do L'Hopital's rule again. Sometimes you have to do it more than once. So that would be the limit as n approaches infinity of 6 over 10, which is 3/5. So because we got a number as an answer for this limit, then the sequence converges, and it converges to 3/5. If we got a limit that didn't exist, then we would say it diverges. Yes,
What's the other one?
the other way?
Yeah, you said there was 2.
Oh yes, there's 2 ways to do this. The other way is whenever you have powers at infinity, when you have polynomials here, is to just look at the highest powers. Because as you're approaching infinity, the only things that are going to be really mattering are the ones with the biggest exponents. You know, if you plug in 1 million, this is a lot bigger than 10 million, whatever that is. What do those reduce to? 3/5. So either way, you'll get 3/5. I didn't teach you all calculus 1, so I don't know where you first learned it. So they give you this messy, scary looking new notation that says, does this sequence converge? But it's really a Calc 1 question, does the limit exist? I'll let you guys try the next 2. Try B and C, see what you get. Oh, there's a D also, B, C, and D. Yes.
Just use the shortcut with the powers, would you?
Yeah, so his question is, if we just use the shortcut and just wrote equals 3/5, would I care? No? I just want to make sure you understand the question. So there's a lot of different ways to get there. I mean, I can just look at it and see it's 3/5 as well. So use the shortcut, that's fine. So we have 2 minutes left. I want you to look at B, C, and D and decide if they converge or diverge. I'm going to write them up here, and then we're going to talk about the answers, and then we'll do the last little bit next time. More vocabulary.
Huh?
I'm dying.
You're done?
I'm dying.
You're dying?
Yeah.
Roll back fully.
I'm dying now, then.
We don't have time for you to die, it's gonna like mess up everything, we're gonna get all stressed out. How are we gonna finish the rest of the semester if you die? We're all gonna be grieving for how many weeks?
Go without me.
We can't.
I'll be
We can't handle the
scared.
grief, Daniel. There's, yeah, we have to take, right, we're gonna miss class to go to the funeral, we can't do it.
You know,
You have to stay alive.
I feel pretty low right now.
It only feels like you're dying.
I'm just really sleepy. It
That's because it's hot in here.
It's not hot. Wait, did you see it was hot here?
is hot in
That
here.
thing was just
blasting full
It was freezing.
Yeah, it was
Okay, I'm trying to
freezing.
give him an excuse for why he
It's
thought he was
hot.
dying. Okay, maybe he thinks he's dying because he's too cold.
No, I'm hot.
It was cold earlier.
I went to the war.
I'm kind of warm now.
Yeah, I'm really
Okay, so you guys looking at those four limits, oh sorry, those three limits?
I'm looking at them.
Okay, thank you, I'm glad you're looking at them. Try looking and thinking. Who thinks the first one converges or diverges? Who has an opinion? It diverges. Why?
Because
E to infinity.
Yeah, that e to the infinity. They're both, it's infinity over infinity, but if you do L'Hopital's rule, this goes to 1 and that one still has an e in it and it just blows up. This one heads off towards infinity. Well, none of that. This one heads off towards infinity, which is why it diverges. So those terms, as you list them, just keep getting bigger, bigger, and bigger. How about this one? Does it converge? Does it diverge? Oh, it's hard. We can't take the derivative of -1 to the n very easily. It converges? Why?
I took a look at Dawes' rule when it was -1 to the n power times the natural log of the absolute value of -1, and that's going to be 0.
Right, so you took L'Hopital's rule. Technically, you can't take the natural log of -1 because it's
Yeah, but it's the absolute
undefined.
value.
it's absolutely.
But the important thing is, what's the numerator doing? What's the word I used for it? It's alternating, right? It just goes negative, positive, negative, positive. What the denominator's doing? It's increasing, right? So you're gonna start with, like 1, -1/2, positive 1/3, -1/4. So who cares about the negative signs? But what are these fractions doing? Approaching 0. So these are approaching 0. This is one where sometimes a graph would help you see what it's doing as well.
So what would we put for that?
We put that it converges. It converges. And the directions do say, if it does converge, what's the limit? So the limit in this case is 0. And what about the last one? We gotta get this one right, then we can go. It converges? What's it converge to? 0? Oh, you don't know now since I asked it as a question? Let's list some terms here.
Okay, it's between 1 and -1. Just switch back.
I listed the first few terms. What's it converging to? It doesn't converge, right? It's not approaching any one number. It's not like eventually they're all really close to 0 or they're all really close to 2. It just keeps bouncing back and forth. +1, -1, positive, -1. It diverges. It diverges because those values are not approaching anything. They just keep jumping back and forth. If it converged, I could say, hey, the millionth term is really close to this number. All I know is it's either a 1 or a -1, but I can't give you which number it is. Right? Okay, we'll finish that last page when I see you guys next time.
So on Tuesday, does that mean that we're gonna have the,
11.1. Am I correct that we finished all 4 parts of example 4, A through D? We left off with definitions and terminology? Okay, and let's also talk about notation. So we talked about a sequence, AN, being increasing. I'm writing this one down, I'm not gonna write all of them down. If AN is less than AN plus 1. This is the definition. What the heck do those symbols mean? gotta understand what the definition means, right? The definition. What's this mean?
The current term.
Yeah, that's just the sequence, how we define the sequence. Like we looked at the one before that was, I don't know, 2 to the n or whatever, where n equals 0 to infinity maybe. And you plug in 0 and 1. So that's just the sequence. But what does this mean over here?
The sequence is less than the sequence plus one.
So you're kind of on the right track. He says the sequence is less than the sequence plus 1.
The current term.
Or the first term is less than the next one.
Aha, so some term, I'm gonna go with, it could be anyway, the first one, but we just start with the first term. So Jake says the first term is less than the second one, right? Because that'd be a 1 and a 1 plus 1. But more general, this is specific. More general is you give me any term, it's smaller than the next one. So for example, the 87th term is less than the 88th term. That's what this means. So it's just a general way of saying that you give me any term, it's smaller than the one that comes next. Does that make sense? The notation? But some term is less than the next one. Well, does that make sense that it's increasing? If we start making up some numbers, I'm going to start with 1. The next term has to be bigger than this one. So someone give me a number bigger than that.
2,
2. Okay, let's not make it too boring now. Let's be creative here.
4.
Okay, we're getting a little more interesting. But, so this term is less than that term, and this term is less than that term, and the next one would have to be bigger.
Yeah.
7 square root of 52, whatever. As long as each one of these is bigger than the next one, that's increasing. Makes sense. You know what increasing means. Increasing means it keeps getting bigger, but it's important that you understand that's what this notation is telling you. That one term is smaller than the next one. Okay, so increasing is exactly what you think it is. The terms just keep getting higher. And decreasing is exactly the opposite. Decreasing if one term is greater than the next one. Right, so if the first term is bigger than the next one, is bigger than that means they're going down. Same reasoning. So increasing and decreasing, let me erase my little examples here. And if it's one or the other, always going up or always going down, then we call it monotonic. Monotonic. Meaning it's always going in the same direction, one direction, always going up or always going down. So there will be questions coming up, we'll do some examples, but also in your homework and in your lab, not and, can't be both, or, that say, is this sequence increasing, decreasing, or is it not monotonic? Meaning it doesn't do either. Everyone okay with those 3 definitions so far? No questions? Okay. And then we have bounded above. Bounded above, bounded below. I'm going to talk about these here in a second. And then just bounded. So the definition for bounded above says a number m exists such that an is less than or equal to m for all n. A lot of notation there. Let's talk about what that means. Anybody want to try to tell me what that means in your own words? And then we can read it. A number m exists. Let's pick a number. 78. So maybe 78 is the number that exists. Such that, what does this mean?
M is greater than or equal to the term.
M is greater than or equal to the term. What were you saying, Joseph?
I was saying A is greater, or A, M is greater than the term, than the number. but it's still increased.
So this is the number, that's my 78 I just made up. Well, I need a little bit more clarity, yeah, Jamie?
Any term of the sequence is lower than or equal to m.
Beautiful. Any term in the sequence, I don't care what your sequence looks like, however many infinite number of terms it has, every single term in your sequence is less than or equal than that number m. It's below it. And this just says for all n, meaning for every single term in the sequence, starting with the first one, going on forever. An example of that might be 8, 4, 2, 1, 1/2, 1/4, 1/8. Can you guys see the pattern? So let's put a pattern there. See the pattern? Divide by 2 every time? Okay, so there's a sequence where every term is half of the one before it. Is there some number, can you tell me some number, that every term in that list is less than or equal to it? There's an infinite number of answers, by the way. What'd you say?
Was it 8?
8 could be one of them. If m equals 8, do we agree that every single term in this sequence is less than or equal to 8? So there is a number that exists. So he wants to choose 8 as his m. So we could say it's bounded above by 8. Think of it as it never goes past that, right? It goes up to 8, but never goes past it, bounded above by 8. I might say it's bounded above by 100. Am I wrong? Is every term less than or equal to 100? Yeah, so there's not just one number, there just has to be some number. A number exists. As long as there's some number that you can say, hey, they're all less than this, then it's bounded above. So when I give a quiz on this or an exam, and I say if it's bounded above, tell me what it's bounded by, some people will say it's bounded by 8. Some people will say it's bounded by 100. You could say it's bounded by 1,000,000. I don't care, as long as you give me some number that they're all less than that. Clear on what bounded above means? Bounded below, almost identical. There's a number they call it little m, and the rest of this is the same, such that, I'll make sure I do it in the right order, that the notes say it. Oh, there's a typo there in my notes. Do you guys have a little m or a big M right there? Big one? Capital? It should be lowercase. We're talking about little m. Little m. Some other number exists, and every term is bigger than that, or maybe equal, for all n. Dot, dot, dot. Is this example I just made up bounded below?
No.
No? You can't find a number that's lower than all of those? I got one person says no. We all agree? Yeah? I'm not going to agree or disagree. You're hanging out there on your own. Nobody wants to agree or disagree with you. So you all agree that every number in this list is less than or equal to 8. So I want to know, can you find a number that all these numbers are greater than or equal than that? Brittany's saying yes. What is it then?
0.
Oh, I like 0. Uh-oh, you just got overruled, Nick. Darn, can't win every time. Bounded below by 0. Those are never going to end up going negative with this pattern, right? I'll never get below 0. It's also bounded below by, someone give me a different number. Anything that they're all bigger than. -1? There you go, now you can just redeem yourself. They're all bigger than -1. What did you say?
Anything negative.
Anything negative, right? As long as you can find some number that they're all bigger than it. So these are some definitions. Increasing means they're always going up. Decreasing means they're always going down. Monotonic, one or the other, increasing or decreasing. Bounded above means there's some number that they're all underneath it. And bounded below that means there's some number that they're all above it. And then finally, just bounded is it has to be bounded above and below. So you'll find sequences that are maybe only bounded below, but then they just keep going up towards infinity. So that would not be a bounded sequence, because it only is bounded on one side. It has to be cut off on the top and cut off on the bottom to be a bounded sequence. Lots of definitions. Let's look at my examples here. We want to look at example 5 here and determine if these sequences are increasing or decreasing or not monotonic, and whether or not they're bounded. So, let's see what we got. Example 5a, an equals negative n squared. Question is it increasing or is it decreasing? If it's neither, then you'd say not monotonic, and then we'll discuss bounded after that. What do you think we should do first?
Plug in some numbers.
Yeah, plug in some numbers. I like to list the first 3, 4, 5 terms just to get an idea of what it looks like. Not all of us can think really abstractly in terms of just looking at the formula. So let's just start with 1. When I plug 1 in here, my first term is going to be
Negative.
-1. What's my second term going to be? -4, right? Because I'm taking 2 in there and squaring it. I get -2 squared. We plug in 1, then we plug in 2. What's the next one? -9. So now we're plugging in 3. -16. Think we got an idea of what it looks like? So the question is it increasing or decreasing or neither? Definitely decreasing, right? They're just getting more and more and more negative as we go. Every term is bigger than the next one, it's bigger than the next one. Right? So it's decreasing. Is it bounded? Yeah? If it's bounded, you're gonna tell me what bounds it above and what bounds it below.
Above is,
Okay, bounded above by 0.
But if you go in negative, it's gonna stop you from,
there's no.
Can you say that louder, Joseph? I couldn't hear you.
just, I was thinking out loud, but I was wrong.
Oh, but you were wrong?
Yeah.
Okay, that's why I couldn't hear you. It's important if you think out loud, because it's often if you're wrong. Bounded above by 0, every single number there is less than 0.
But then it's also gonna be, greater than negative,
That's not a number.
that's not the number.
I need a number. If it's bounded below, you need to give me a number. That every single term is larger than that. Infinity is not a number. So can you find a number? You might go over here shaking his head. There's no number. No matter what negative number you give me, there's going to be another term that goes below it. Right? It just keeps getting more and more negative. So it's not bounded below. It just keeps getting more and more negative, large negatives. So then let me ask my question again. Is this a bounded sequence?
No.
No. It has to be above and below. So this is not a bounded sequence. We good? Okay, try the next one without me. See if we agree. The next one, I'll erase this example. 5b says that an equals -1 to the n plus 1. I want the same questions answered. Is it increasing or decreasing? And is it bounded or not? Write it down on your paper. We'll see if we all agree here in a second. Few terms,
Yeah, one,
starts with 1, the next one's -1. That's the alternating that Joseph was talking about.
so then it would be,
So it's not increasing, right, because this term is smaller than that one, so definitely it's already a problem right here. It's not decreasing, even though from here to here it went down, but from here to here it didn't continue to go down. So it's not increasing or decreasing, so we write not monotonic. That just means it's not increasing or decreasing. Is it bounded?
Yes.
Above and below?
Above and below?
Yeah, is it?
Yes.
So it's bounded. So if you're gonna tell me it's a bounded sequence, you're gonna tell me some number it's bounded above by and a number it's bounded below by. Above by 2? Okay, so I like Joseph's answers. Anybody have different ones? 1 and -1 would have worked as well, because these are all less than or equal to 1 and greater than or equal to -1.
what about 0?
0?
Yeah.
Are they all greater than or equal to 0? Or less than or equal to 0? See the problem? 0 is like, you can't say all of them, so it's not bounded by 0. A visual kind of helps. You think about if we were to graph these, n and my an's, I'll give you a little visual. So the first term for n equals 1, let's just make this a 1 and a -1. The first term is here, the next term is here, then the next term, and it's alternating, right? It'll keep doing this all day long. Here's my little terms, 1, -1, 1, -1. The visual is, can you find some number that all of these are below it? It's bounded above by some number. I just drew in the 2 that Joseph gave me. And are all these numbers above something? And so it's like the whole sequence is trapped between those two. So you could have drawn them up here, you could have said 1.5, but you couldn't go anything closer than 1 to -1. If you'd said 0, they're not all either above or all below. So bounded kind of tells you they're trapped inside a little box that goes on infinitely forever. So it is a bounded sequence, but it's not monotonic. So what about C? I got lost over here in my picture. What about C? Are you gonna pass this one, Daniel? Maybe? Maybe?
I get it now.
You get it now? Oh, that's good. This is why we have this conversation, so hopefully everyone gets it. Let's list the first few terms. 2, 1/2, 2/9, 1/8. These are reducing, I like it. What's next? I lost my place. 2/25. I said 18th, that's not right. 8. I was reducing it in my head. Now, when you reduce your fractions, it is often difficult to tell if it's increasing or decreasing, because most people, including myself, can't look at, 2/9 and 1/8 and 2/25 and totally just look at them and tell if they're increasing or decreasing. So quite often it helps not to simplify when you're looking for that pattern. So if we hadn't simplified, it would have been 2/1, 2/4, 2/9, 2/16, 2/25. If you don't simplify, it's a little bit clearer. So you can see then that the numerator's always staying the same. Because my denominators keep getting bigger, that tells me that this is doing what? Decreasing, right? Because the denominators are getting bigger. Hard to tell up here. Now, if I had asked you to list the first few terms of the sequence, you would have wanted to simplify them, and these would have been your answers. But it helps to look at it in this form to tell that it's decreasing. Is it bounded? Above or below?
Above and below?
Above and below? Above by what?
1,
What?
1,
Oh,
Plus
Plus
2.
2.
okay, I'll go with 2.
Okay.
Right? I like the 2 better, because this one's not below 1. So, bounded above by 2? Because every term is less than or equal to 2? And below by
Zero.
0, everything's positive here. So this one is a bounded sequence. Because it's bounded above and below. There's other answers you could have put here. As long as you can come up with a number and it's true, we're good. I want to draw a picture of this before I talk about that next theorem. Well, let's talk about the theorem first, then we'll do the picture. It goes together. So the theorem says every bounded monotonic sequence is convergent. What does convergent mean? It's been a while. Couldn't hear you, Joseph. Were you thinking out loud or were you answering?
Like it'll collide, like it'll touch something.
It'll touch
a
something.
specific point.
Okay, I kind of think I know where you're going, but I need a little bit more detail than that.
It has an answer.
What has an answer?
To convert.
The what?
The graph function.
The graph, the function? We're dealing with sequences here.
Converges to-
Convergence gets closer and closer to a number.
So converges means those terms get closer and closer to a number. The limit, converges means the limit, as you go further and further out in your sequence of your terms, it equals some number, some L. That limit exists. So as you go further and further out, maybe your numbers are all getting closer to 8, and then it would converge to 8. Or if you're like the one that was going more and more negative, -4, -25, so forth, that's just getting more and more negative, not going towards any number. So we would say that one diverged because it's not heading towards a number. So the question is, or the definition of convergent was this, and the theorem says, if it's every bounded monotonic sequence is convergent. I want to draw a picture of this one, a graph of this one, to make sense of that, because that one's bounded and monotonic, correct? So that particular one, and started at 2, right? So the first term was 2. The next term was 1/2, roughly here. The next one was, I can't see it, 2/9, which is pretty small, maybe down here. And then I'm at 1/8, which is over here. And I don't really even need to know exactly where they are, because what we decided over there was that this sequence is decreasing, and we had it bounded above by 2, so it's not going above this, and it was bounded below by 0. So these have to decrease. I want to draw another line in here, another color. Hang on. These have to decrease, but we already know they're not going to go above this or below this. Right? So I'm going to keep drawing them. They just have to keep getting smaller and closer to this 0 without touching it, right? So therefore the limit has to exist, because they just keep getting closer and closer and closer and closer to this bound. So it must converge to something. Because the decreasing, the bounds keep it inside here, and then if it's always decreasing, you're going to run into a roadblock, and the roadblock is where you're going to converge. Does that make sense? What would have been different if it was increasing?
It would have converged to 2 instead.
Yeah, it would have converged up here to 2. It would have gone up to 2 instead of down to 0. Now, it doesn't always converge to the number you chose, but it converges to the smallest one you could get. You know how we said it's bounded above by 2? We could have said it's bounded above by 10. You're not guaranteed to go to, but you take the ones closest to the edge, it will always converge to those. So I like the visual to explain why, if it's bounded and monotonic, it will converge for sure. Because it gets closer and closer and closer to that lower bound or upper bound. How do we feel? All right, definitions? Okay, here comes some weird notation. Let's see if we can handle it. The notation gets scary, but once you get used to it, it's not so bad. example 6. It says that some sequences are defined recursively. Those of you who do computer science, you probably already know about recursion. Recursion means that one term depends on maybe the one before it or maybe a couple before it. The formula that we're looking at, this is called the Fibonacci sequence, it actually says this. Kind of a detailed explanation for this formula. I want to make sure I write it exactly the way they have it here. Oops, -1. Plus an minus 2 for n greater than or equal to 3. So this is the definition. It's a lot messier than, say, just this. When we had this definition of the sequence, we could plug in 1, we could plug in 2, we can plug in 3, and list all the terms. This is the same thing, but you can't just plug in any number, because if I want, say, if I wanted the 7th term right here, the 7th term, I just pick 7 randomly, what would I do if I wanted the 7th term? If I want A7.
2 over 49.
2 over 49, right? Just plug the 7 in there. Totally easy. 2 over 7 squared is 2 over 49. If I want the 7th term over here, well, I know the first term and the second term, they gave me those. But then I have this formula here for any n greater than or equal to 3, which 7 is. So this says that if I want A7, if I want A7, I have to do, what's this then?
A6.
It's A6 plus A5, right? 7 minus 1, 7 minus 2. So to get the 7th term, I have to add the 6th and the 5th term, which I don't know either. But this is what we mean by recursively defined. This term is defined by the 2 before it. And if I want to get out, say, to the 100th term, if n is 100, I would have to know the 99th term and add it to the 98th term. What'd you say?
Oh, it's like bowling with strings.
Well, it is like bowling, you're right. Where depending on how you do, you get to add the ones before it. Genius, I've never thought about that before. We all need to go bowling now. That'd be fun. So much more fun than doing calculus.
We
Or
do
maybe
for a
not
final.
quite.
Hey.
For the final exam. I'm gonna see if I can work that in. I'm gonna put a bowling example in. Okay, if you haven't been bowling, you don't understand how the scoring works, in which case you don't get it. Which is why we all need to go. Some people have never bowled. Anybody here never go bowling before? So Maribel's never bowled, so she doesn't even know what we're talking about.
asked if the class bowled today.
All the reason we have to go.
Both my teachers asked.
Okay, so are we okay with this part? So let's list a few terms here. The directions just say find the first 10 terms. So I'm going to list my n's here. So I want the first, second, third, fourth, fifth, sixth, I'm running out of room, 7th, 8th, 9th, and 10th terms. What's the first term? What's A1?
There's 1.
It's 1, they gave us that one. A1 is 1. So there's no plugging in, they just told you what the first term was. What's the second term?
Also 1.
It's also 1. But now I'm on the third term. A3. If n is greater or equal to 3, I have to use this formula. So A3, according to this formula, is
1 plus 1.
1 plus 1, you're a step ahead of me. A2 plus A1? You agree that's what the formula tells me? To get the third term, I'll have to add the second term plus the first term? Good news, we already know what those are. Here's the first term, here's the second term. So the third term is the sum of those two. So it's going to be 2. 1 plus 1. What am I going to do to get the fourth term? Because they already sees it. I can tell by the smile, it's like I can get this.
Yeah. It's 1 plus 2.
1 plus 2. If I want the fourth term, all right, one more time here. If I want the fourth term, if n equals 4, I have to take a3 plus a2. Let me restate this in words. Any term is the sum of the two that came before it. Right, these two came before this one. So here's this one and this one were given to us. This term is the sum of these two. This term is the sum of these two. So 1 plus 2 is 3. Find the rest of them. Can you find the rest of it? We're going up to 10. Everyone clear? If you're not clear, ask a question of your neighbor, of me. I want you to list the first 10 terms of the sequence. And if you're not sure how to do it, then this is a perfect time to ask a question. It's about understanding this notation. Got them? 10 of them? Maybe? Ooh, Daniel's like almost sounding positive now. I like it. So we already did the first few. We had 1, 1, 2, 3, and 5. Oops, I just gave it away. Darn it. The next one you got hopefully was 5.
Yeah.
And then 8, 13. Is
21, 34, 35.
that 10?
Wait, how did we get the first one?
This one?
Yeah.
Aha, that one was given to us. So it says here, the first term is 1, and the second term is 1. They had to give you those first two,
Yeah.
because how else would we have been able to do this without having 2 to start with? That's why this formula only works for n greater than or equal to 3. So they'll give you those first few terms, however many it might be, and then the other ones will depend on those. So the Fibonacci sequence is actually really cool. It shows up everywhere in real life. Seashells, plants, pine cones, everywhere. You'll have to Google it on the break. Break's coming up soon. I'll try to use my artistic abilities and show you what the Fibonacci sequence, how it shows up in real life. I don't understand why it works, why it shows up, but it does and it's really cool. So imagine I've got a little square here whose side is length 1 inch. So there's my first term, that's 1. And then my second term is also 1, so there's another square of the same size. Now, my next one has to be a square whose sides are 2 wide instead of 1, right? So this is a 1 by 1 square, so my next one's going to be a 2 by 2 square. Right? It's twice as wide, twice as tall. They're supposed to be squares. Humor me with my artwork.
Use it in art.
It's in art, yeah.
It's a spiral.
You got it. And Nautilus shells, everything, even I don't know whether or not you're religious.
Perfect.
God's art or whatever.
That's the
Yes.
golden ratio, isn't it?
Yeah.
Yeah, golden ratio shows up in there. Yeah, so you've got 1, 2, and so then my next one is 3. So I need to draw a square that's 3 by 3. Well, this distance right here is already 3. So I'm going to, that's a 3 by 3 square, right? 3 by 3. The next one has to be 5. How convenient. This is 2 plus 3. So there's a 5. I can attach it to this guy. I'm trying to make him look square. 5 by 5. The next one has to be 8 by 8. But this is 5 plus 1 plus 2. So that's 8 going across. So here's a square here that's 8 by 8. I'm doing a fairly good job of making these square. I just want to point that out. A little proud of myself at the moment. This side here is actually 13. So I have another square here. Okay, I'm going to run out of ability here any second now. Oh, I missed. Darn it. Start down here. There we go, 13 by 13, and so forth. Now, the next one, I can't fit on the board, it's gonna fall off the bottom over here, but it would be 21 by 21. Watch what happens when you connect the corners of these terms. So if you start with this inside corner of this very first box I started with, and I'm going to connect it to its other corner, and connect to the other corner of that one, always across the diagonals. I'm going to start here, go diagonal, and go diagonal, then I'm going to go diagonal over here, then I'm going to go diagonal over here, right, always going diagonal across each box, so I'm going to go from here to here, there to here, connect this diagonal to that diagonal, across that, that's not a straight line, it's supposed to be curved, sorry. Connect to this one, connect to this one, connect to that one. It actually creates a spiral. That's the same spiral you will see in seashells, pine cones, flowers, everywhere. And it goes along with the Fibonacci sequence. Fibonacci, you have to Google him, pretty smart dude, figured this out. How, I don't know. Back before they had anything else to entertain themselves, they had math. And some of us think it's entertaining. What'd you say?
So it looks like square, they use squares as.
Yeah, but the spiral is the cool part. The spiral is the cool part. If you like Google the Fibonacci sequence, you'll see these spirals everywhere when you look at the images and so forth. So that's the Fibonacci sequence. That's just one very specific, recursively defined sequence that has a name, but there's an infinite number of recursively defined ones. We can make up other ones sometime if you like. Over time. I don't know if you have room under example 6. I just want to point out that it could be all kinds of different recursive. There's only one example in our notes, so I'm going to show you one more here. So maybe we're told that the first term is 1, the second term is 3, and the third term is 4. And then we're told that an equals an minus 1 minus an minus 2 plus an minus 3 for n greater than or equal to 4. This is another example. You can't draw a picture for this one, I made it up. Another example of a recursively defined sequence. You're given the first 3 terms and then told how to find any other term based on the ones that come before it. So this is some term, this is the one before that, the one before that, and the one before that. So if I want the 4th term, this says I'm going to do what? To get the 4th term.
The third.
The 3rd term minus the second term plus the first term. You see that? So for this particular one, if I'm listing my terms, I like to put them in order here. Here's 1, 3, and 4. To get the 4th term, the 4th term is going to be the 3rd term minus the second term plus the first term, which is 2. What if I wanted the 6th term? What if I want a 6? What do I need?
Fifth.
I have to have the 5th term, right? Because the formula tells me to get the 6th term, I have to take a5 minus a4 plus a3. Using this formula, right? So I can't, when you have a recursively defined sequence, you can't jump ahead and find the 6th term without the 5th one. So we have to go find the 5th one first, and then get the 6th one. And if you wanted the 85th term, you'd be sitting here a while, waiting to see what it's going to turn out to be. I don't know. Maybe there's a pattern. Sometimes a recursively defined one has another pattern that's nicer, but not always. You have to find each term in order. How are we doing? All right? Okay, I'm going to introduce series and then we're going to take our break. And An introducing series requires my beautiful piece of yellow paper. So I want you to flip over to 11.2, which is on page 170.